In this section, we're going to be covering Gauss-Jordan elimination, which I would argue is probably the best technique for solving matrices. It can be used for any size, doesn't matter how big it is, what shape it is. It could be square, it could be rectangular wide or rectangular tall, but it can basically solve any type of problem. There's no conditions that need to be satisfied with like other techniques we're going to learn in the future, such as the inverse method or even Cramer's rule. And Gauss-Jordan elimination just basically says, you know what? I have a technique that just does it for you. It may not be the nicest one. It's kind of like the quadratic formula, but that's gonna always work for you. So that's kind of the best part about it. So given a 2 by 2 system of the form, so imagine you have a system and instead of giving you like A, B, C, D, E, F, and all that, we're going to start labeling using subscripts. So the first number is the row, and the second number is the column. So A1, 1x plus A1, 2, y equals B1, and then A2, 1, because this is equation number 2, which will be row 2, x plus A2, 2, y equals B2. Forgot the 1 right there. And so the idea here is we know elimination method. We know substitution method. They work perfectly, but they can kind of get really overloaded when you're dealing with large systems. So what if there's a way that we can kind of just focus on the true aspect of what's important, which is the numbers, and kind of be able to do all of those manipulations in a very compact way. And so that's kind of what happens with elimination method, or sorry, Gauss-Jordan elimination. So essentially, what we're going to do is we're going to take this system and we're going to convert it into a matrix, right? So we're going to do convert to matrix. So the question is, how do we do that? Well, we have a special type of matrix that will allow us to basically take this system and make it into something that we can work with. And so the idea is this. We start off with our left bracket, and then the first column represents the x variable. The second column is the y variable. And you just put the number in front of each letter. So A11, A21 for x, A12, A22 for y. And then the equal sign, we could put like equals equals, but that doesn't look very nice. So some mathematicians adopted the vertical line notation. So that's what we're going to use. And from there, we're going to put our b values. So b1, b2. So basically, I've gotten rid of all the pluses, the equals, and I've made it just this one nice matrix that I can work with. And we call this the augmented matrix. So you're going to want to do this basically for every single problem. So the augmented matrix. And so our main goal is going to be converting that into a solution, right? And so the question becomes, how do we do that? So we will turn any linear system into an augmented matrix and then reduce it down to a solution. Okay. So what is the method of doing that? Row operations, right? So row operations will be how we do that. So effectively, we have a goal, okay? Our goal is this. Our goal is to turn any matrix into a reduced form called row reduced echelon form, which is abbreviated as RREF. Okay. Now, what does that mean? It's just a very specific type of matrix that has four certain characteristics, right? And those characteristics kind of not too bad to understand. Number one, all rows of 0 at bottom. Number two, the first non-zero value in a row is to the right of the first non-zero value above it. I call this the staircase property. Number three, the first number in each row is 1. And then number four, any column with, sorry, let me say it this way. The column with the first non-zero value, basically the 1, has zeros above and below. Now, when you hear all of these conditions, you might think that's a lot to remember, and it kind of is the first time, but the good news is, for this class, specifically Mat 211, it's really going to look one or two different ways, right? So if you think about each condition, essentially, RREF forms, they're going to look like this for this class. You're either going to get 1, 0, 0, 0, 0, sorry, 0, 1, 0, 0, 0, 1, and then some numbers, okay? So that's the first way you'll see it. And we call this the unique solution, okay? Or you'll get something like this, 1, 0, 0, 0, 1, 0, and then maybe you get something like this, right? And then you get like a number right here. Now, it's not exactly going to be, this could be any number, okay? But I'll just put like the number 2. So if you get something like this, and to be honest, you could even have numbers right here. As long as this bottom row looks exactly like this, and it has to look exactly like this, what this is the no solution case. So this is no solution, because the bottom is saying 0 is equal to 2. That's essentially what it's saying. And if you go back to the first one, the first row is always column. Second column is y, third column is z. So the first statement says x equals some number, y equals some number, z equals some number, right? Like that's why it's a unique solution, because each row only has one letter and is equal to a number. Now, those two tend to be not too difficult to kind of wrap your mind around. It's the infinite solution, which is the one that often confuses students, because what you'll end up running into, mainly in this class, is there's several ways that we can see it, but the key thing that you'll run into is, because we're dealing with 3x3s, you're going to have a row of all zeros, okay? And so maybe you have a 1 here, and then, well, you have to have a 0 here, and then like a number and a number, right? And then some number here, and then some number here. The bottom row is saying 0 equals 0, which is a true statement. So that means there are infinitely many solutions that could satisfy this equation. We actually have a name for that column. It's called a free variable, but in this class, we don't really focus on that idea. So this is the infinite solution case. So we're going to have to learn how to deal with each of these. Like, our goal is to make any matrix, like the one I gave above, look like this. Now, this was for 3x3. For 2x2, I should have done 2x2 first. So let's do 2x2 now. It's either going to be 1, 0, 0, 1, some numbers. So that's unique. It's going to be 1, some number, maybe. It could be 0. 0, 0, and then some number here. That's not 0. And then some number here. That's none. I'll just put like the number 2 just to make it obvious. And then for this one, it's going to be 1, some number, 0, 0, 0, some number. So we're going to have to learn how to deal with these three different cases, right? Unique solution, no solution, infinite solution. So the question becomes, okay, I have a matrix right here. How do I make it look like that? Well, row operations do. So row operations are how we get from our first matrix to our last matrix, right? So the three row operations are as follows. Number one, you can row swap. So most people will do a double arrow and they'll say which two rows, row one and row two. Then we have what we call row scaling. So we can multiply a row by any number except 0, okay? Because then the row becomes all zeros. And then number 3, we have row addition. So we can take one row, add it to another, and basically modify that row with that other row, right? And you can multiply the rows by a number too. So those are the 3 row operations. So let's just practice by solving a system into using these row operations. So here's the basic idea. But here's the best part. You can do this all on your calculator. And once you get comfortable with the calculator, these problems take 10, 15 seconds. So solve 2x plus 3y equals 1 and 5x plus 4y equals 6. Okay. So this is the equation that you want to solve. And just to make this one a little bit simpler, I'm going to make this a 6. Actually, let me do this. Let's make this a 3. And let's make this a 6. That'll work. So step number 1 is you're going to want to augment. So augment the matrix. So the first part is going to be the numbers 3, 5, 3, 3. Sorry, 4. Equal sign 6 and 6. That's your x, that's your y, that's your equal sign. Okay. If you can, this is not a requirement, but if you can, make the top left corner the number 1. You don't have to. Like if you can, go for it because it'll just make your life easier, especially when the matrix gets bigger. But your goal, essentially, okay, this is your goal. You need to make this a 1. Okay. You want to make this 0, the 5 a 0. You want to make the 3 a 0. And then you want to make the other 4 a 1. Because you want to make it look like 1, 0, 0, 1. Now, you will run into a problem where that's not possible. But whenever you enter in a problem, that's where you start. You want to make it look like 1, 0, 0, 1. Okay? So that's going to be our frame of reference. So step 2, we're going to do row reduction. So I'm going to take this and I'm going to multiply row number 1 by 1/3, or you could divide it by 3 if you want to do it that way. And so I get 1, 1, 2, 5, 4, 6, right? I didn't even talk about row 2, so just write it down first. If you don't mention a row, I'd always write it down first. Okay, the next number I want to eliminate is this 5. I want to make 0. Okay, so how do I do that? I'm going to multiply row number 1 by -5 because -5 plus 5 is 0. And if you really think about that, that's just an elimination method. So we're actually doing an elimination method just without all the pluses and minuses. So -5. And then we're going to add that to row number 2, and that's going to become my new row number 2. And so if I multiply row 1 by -5, and then -5, -10, and then I didn't do anything to row number 2, I'm going to add those together, and I get 0, -1, and -4. So this begs the question, okay, you multiplied row 1 by -5. Do I have to write down -5, -5, -10? You don't. That was I call it a temporary change, meaning we don't actually have to keep it. So you can write down the original row number 1 because the row that I am actually changing is row 2. So that one will look different though. And we found it as 0, -1, -4. Okay. So we're getting closer to becoming 1, 0, 0, 1 number, right? Like that's our goal. So could you divide row 2 by -1? Yes, but I'm going to save that for later because what I'd rather do is add row number 2 into row number 1 to create a new row 1. So 0, -1, -4, 1, 1, 2. You do have to be very careful. It's very easy to copy the wrong matrix down, add numbers incorrectly. Like 0 plus 1 is 1, but sometimes you might say 0 plus 1 is 0 because you're thinking multiplication. Just got to be careful. So 1, 0, -2. So that's my new row 1, 1, 0, -2, 0, -1, -4. Almost there. Now I'm going to multiply row 2 by a -1. And so that becomes 1, 0, -2, 0, 1, 4. And so this is my x value. That's my y value. So x is equal to -2, y is equal to 4. And that's row reduction. And so if you plug this into your calculator, second matrix, go to edit, and then we do 1 by 1, put a 0 in there, and then we do 2 rows, 3 columns, because we need that 1 for the extra one. Starting with the original one, 3, enter, 3, enter, 6, 5, 4, and 6. Okay, so one more time. If you want to get to a matrix, you do second, hit the X inverse button to do matrix, hit the right arrow key 2 times to edit. That's how we edit a matrix. We press enter. The first number is the rows, the second number is the columns, and then we type them all in. And then from there, we quit second mode. Then we do second matrix. Hit the right arrow key 1 time, and then scroll all the way down until you find the one that says RREF. Not REF, but RREF. Press enter. Second matrix, A, close parentheses, press enter, and we got our answer. So theoretically, you could do all of these problems on your calculator instantly to get the correct answer. So that is a unique solution. So x comma y is equal to -2 comma 4. So this is what we call the unique solution, meaning one solution. And remember, all linear systems either have one unique solution, infinite solutions, or 0. There's no other option. It's not 2, 3. It's just 1, none, or infinitely many. So if we do another example where maybe you get a matrix that looks like this, solve the system. (2x plus 3y equals 6, and -x plus 3/2 y equals -3/2. Okay. Fractions are very scary with these, but you could always kind of get around them. So step 1, augmented matrix. So 2, 3, equal sign, 6, -1, 3/2, -3/2. This is your x, this is your y. And just to show you this, you could go straight into your calculator. Second matrix, edit, press enter, enter, enter. 2, 3, 6, -1. 3 divided by 2, -3 divided by 2. Second, quit, second matrix, math, up arrow to get there faster, RREF, second matrix, A, and there's my answer, 2.25 and 1/2. We're done. That's how fast the calculator does it. But if we do it by hand, step 2, row operations, I know we like the number 1, but I don't like fractions. So what I'm going to do is I'm going to multiply row 2 by 2 to make it much nicer. So row 1 wasn't mentioned. I write that down first. -2, 3, -3. And then I'm going to basically make this number 0. Like I said, I don't want fractions. So if I can't get the number 1 in the top left corner, I will wait till the very end to do that. Like I said, it's not worth getting fractions over it. So I'm going to add those two together. So row 1 plus row 2 is my new row 2. So row 1 is my temporary change, which I didn't do anything to, so I'm going to rewrite it. And then if I write down these, I'm going to add them together. I get 0 and 1. Oh, sorry. This should have been a minus sign. Sorry. That's a minus sign. So put a minus right here. There we go. That makes more sense now. Minus, minus. So then I get 0 and then I get 2. So 0, 0, 2. And then you recognize, oh, look at that. 0 equals 2. No bueno. No solution. You don't have to go any further. You can stop right there because you just ran into the no solution case. So that's the no solution. So far, if you go back here, we've done unique, we've done no solution. So then how do we deal with the infinite solution? So that's going to be the most annoying one because you have to do a little bit of extra work in order to be able to solve it. But fundamentally, it's not the worst thing, okay? So let's do an example. Solve the system. 2x plus 2y equals 5, and then 6x plus 3y, sorry, not 3y, 6y equals 10, like that. You can actually tell when it's going to be an infinite solution when the equations are just like multiples of each other. That's kind of a trick to it. Step 1, augment. So I'm going to augment 2, 2, 5, 6, 6, and 10. X, Y, like that. Step 2, RREF. So you will have to row reduce this all the way because you are going to be doing an extra step after it. So I'm going to multiply row number 1 by 1/2. But I don't like fractions, so but that's okay for this one. This is the one where I'll be okay with the fraction. So 1, 1, and 5/2 or 2.5. If you can convert to decimals, do it. And then 6, 6, and 10. And then I'm going to do negative row, sorry, -6. Actually, you know what? In this case, not worth it. I take it back. I'm just going to go straight into the row addition. So this is what happens when you have to manipulate a row. Again, -3 row 1 plus row 2 is my new row 2. This is going to be much nicer. So I get -6, -6, and -15. Oh, I see what, that should be a 15. There we go. That's supposed to be 15. I'm just gonna write that down. And then 6, 6, and 15. There we go. If I add these together, 0, 0, 0. So no changes there. We only did that temporarily. And then we got 0, 0, and 0. So we now match the infinite solution case. So how do we deal with this? Well, once you get to this point, step 3 is going to be rewrite equation. So you're going to want to rewrite your equation. And so we're going to do, well, actually, yeah, that's fine. Let's divide it by 2. Now we'll do that because we want to be an RREF. So 1/2, 1, 1, 2.5, 0, 0, 0. There we go. So then now we rewrite the equation. So the way that we express this answer is called parameterization. So we want to parameterize the variable. And so essentially what we're going to do is rewrite the equation x plus y equals 2.5. And so the solution is x comma y, okay? X comma y. So if we solve for y, so step 4 is going to be solve for y. So x plus y equals 2.5, y equals 2.5 minus x. So what I could do is I could say x comma y is equal to x comma 2.5 minus x. And so effectively what I did is I replaced this right here with that right there. And so now I've rewritten my answer in terms of one variable, which is very helpful. So we call that parameterization. And so that's one of the things that you're going to have to do when you're solving for infinite solutions. Now, if you're wondering, why would I want to parameterize? The idea behind it is rather than you having to think of two numbers that work perfectly, if you give it one number, it'll create the second number that'll work. So let's just pretend, hey, let x be equal to 0. So then that means x comma y is equal to 0 comma 2.5, right? I only had to think of one number. So then if I plug this into my equations, right? 2 times 0 plus 2 times 2.5 equals 5. Well, that means 5 equals 5. Check. 6 times 0 plus 6 times 2.5 equals 15. 15 equals 15. Check. So it'll always generate a correct solution, which is good. So that's row reduction in a nutshell. Let's do one more example. What happens when we have something where it's not square? So solve the system, because it doesn't have to be square. It could be rectangular, meaning more variables than equations, or even more equations than variables, which those are kind of a weird problem. We call those overdetermined systems, which typically don't have solutions. But something like this will. So if you run into something like this, you essentially have what's called an underdetermined system, more variables and equations. So you'll always have infinite solutions, or maybe no solution, but never unique. So step 1, let's augment. So 1, 1, -1, -1, 6 and 7, and then 4 and 7. Okay. Now, this is very important. This is a good example to illustrate this. Your goal, because if you go back to the definition of RREF, the column with the first non-zero value has zeros above and below it. We call those pivots. When you're row reducing, you only have to make it into that RREF by making the number above and below each of the, I call them like the first place leaders of the row, have zeros above and below. So what do I mean by that? I want to eliminate this number first. So we're going to eliminate that and make it a 0. So negative row 1 plus row 2 is my new row 2. And so we get -1, +1, -6, -4, and then 1, -1, 7, 7. Now, row 1 is not going to change permanently right now. That's just a temporary change. If I add these together, I get 0, 0, 1, and I get 3. Okay? So this is important. This -1 right here, you can't do anything to it because since it's not the first number in a row, we call it a free variable, meaning it just hangs out. You don't have to really pay attention to it anymore. But what number I do need to eliminate is the number above and below the first place leader. So this 1 has to get a 0 above it. So we're going to eliminate the 6 now. So -6 row 1 plus row, sorry, the other way, row 2 plus row 1 is my new row 1. So 0, 0, -6, -18, 1, -1, 6, and 4. Okay, so row 2 isn't changing anymore. And then row 1 becomes this. and then negative 14. So now we have it in RREF. Now, when it comes to these matrices, again, you could just plug it into your calculator, second matrix, go to edit. This is going to have 4 columns, not 3. So it's going to be 1, -1, 6, 4, 1, -1, 7, 7. I would highly recommend that you learn how to use your calculator with these. And as you see, we got the same thing, right? At least you learn how to use your calculator for the RREF. Now, we're going to rewrite a system. So I have 2 equations. X minus y equals -14. And then z is equal to 3. Okay? Step 3, solve for y. Okay? Solve for y. And z. Now, if you're wondering, why am I not solving for x? In this class, we parameterize around x. So x is going to be the function variable. So it's always going to be every other letter but x. So x minus y equals -14. Negative y equals -14 minus x. Y equals 14 plus x. Okay? And then z is equal to 3. Step 4, solution. So x comma y comma z is equal to x comma 14 plus x, because that used to be y, and then 3, because that used to be z. And that's the parameterization of it. Now, again, we'll do one more example where it's a huge matrix and you just have to use a calculator. You really, really don't want to do this by hand. So let's do that real quick. Solve the system. So if you have something like this, x plus y plus 3z equals 2. Actually, I'll even do the spacing. Sometimes they don't do that, but why not? Y plus 6z plus w equals 9. X plus 3y plus 9z plus 2w is equal to 11. X plus y plus 3z plus w equals 2. Okay, so that's our system. If you can do this one by hand, you could do any of them by hand. This is like the overkill. So step 1, you still got to augment. So x, y, z, w. So 1, if you're missing a letter, you put a 0. 1, 1, 3, 1. 3, 6, 9, 3. 0, 1, 2, 1. Equal sign. 2, 9, 11, 2. Step 2, RREF. So we're going to use our calculator. Second matrix. Let's do edit. I'm going to do a 1 by 1. Put a 0. And then I have 4 rows, 5 columns. So one at a time. 1, 1, 3, 0, 2. 0, 1, 6, 1, 9. 1, 3, 9, 2, 11. 1, 1, 3, 1, 2. So we've typed in all the numbers. And then we do second quit, second matrix, math, up arrow key for RREF, second matrix, hit A, and there it is. That's my answer. I'm done. So, you know, if you had to do this by hand, which on an exam, they would not make you do one like this by hand because it would take too long. By calculator, very fast. So right here, that's X, Y, Z, W. So -2.5, comma 0, comma 1.5, comma 0. If you ever want to convert it to a fraction, math, frac, there you go. That converts it to a fraction. Now, last type of problem they can give you, honestly, is rather than making you do all of that work, they say, you know what? I'm going to give you the answer. I'm going to do the RREF for you. You tell me the answer. So example, given the RREF, what is the solution? So something like this. So if I gave you something like that, well, this is unique. So my answer is 5, 3, x and y, x and y. That's it. You're done. The unique one's pretty, just, the numbers are there, right? Given the RREF, what is the solution? So what if it looks like this? 1, 2, 4, 0, 0, 0. Sometimes, again, in the homework, I noticed that they don't use the vertical line. So the last column is the b value. So just pay attention to that. So this is x and this is y. Well, you're going to rewrite it into an equation, x plus 2y equals 4, because that's your equal sign. And then you're going to solve for y. So 2y equals 4 minus x. Y equals 4 minus x divided by 2. And so what you end up getting is x comma y is equal to x comma 4 minus x over 2. And you have just parameterized the solution. And so the biggest thing I can recommend for you in this section is learn how to use the calculator, because in the big ones, you really need to use the calculator. And then this last problem is really the most important one, because this is actually how you get the answer, right? If you can't read what the final result is doing, then the row operations don't really mean anything. So really understand the different solution types, because that's probably the most important thing for this section.